thanks all for coming, and thanks for the organizers for inviting me for this. So my talk today will be about addressing some of the issues we have with the use of antibiotics in aquaculture, and I'm going to present some solutions to where we can try to reduce the use of antibiotics. So just to put some context here, so why is this important? We have a growing human population. The requirements for high quality protein is increasing, and this is so supporting protein for human consumption is an issue that we have to face and a major challenge in the future. So one of the solutions for this, and already a very important contributor to food consumption in the world, is aquaculture. There are a number of advantages with aquaculture relative to other food-producing sectors, and one of them is that it has a relatively low carbon emission. So the carbon footprint of aquaculture is lower than for the other types of animal production. You see there's 3.5 kilograms of CO2 produced per kilogram of protein relative to 20 kilograms for cattle production. Another advantage of aquaculture production is the efficiency in feed conversion into food. So here we have the feed conversion efficiencies. You see 61 kilograms of meat produced per 100 kilograms of feed, which is much higher than the other types of animal production. So there is definitely some potential in developing and expanding aquaculture because it is, relative to other food-producing sectors, it is a more sustainable solution. When we look at the global protein production right now, you can see that the high-emission producers are making up about 25% of our protein production, but they're responsible for 70% of the carbon emission. So there's something, there could be some benefit in transforming some of these high-emission producers to more low-emission producing. Aquaculture is already now an important food-producing sector. It's the fastest-growing food production in the world. If you compare that to capture fisheries there on the bottom, that has been stable for centuries, whereas the aquaculture is definitely increasing and is predicted to continue increasing. Right now, to give you some numbers, so global aquaculture is producing about 131 million tons with a value of about $300 billion US. 57 or more than 57% of the aquatic animal products that we use for consumption is coming from aquaculture. So this is a super important sector that contributes a lot to our high quality food production. Also, Chile is an important player in the aquaculture. So Chile is among the 10 world's largest aquaculture producing nations. In 2022, about 1.5 million tons of fish with an export value of $8.5 billion US. And this is an increasing trend. So we see an increasing production of fish in Chile with a substantial contribution to the income of the country. But there's always, of course, some issues with this. So if we want to expand aquaculture, which has some potential, we need to think about some of the issues that we also are facing in this industry. And one of those is diseases. So fish become sick like any other organisms, and two of the most important fish diseases in aquaculture is shown here, so Vibrio angularium and Flavobacterium saccharophilum. These are globally occurring fish pathogens, so they infect and kill the fish. They cause high mortality, especially in the early stages of the fish production, so the larvae and the fry. And the current treatment option for these diseases is the use of antibiotics, right? And so we're concerned about the spreading of antibiotics and antibiotic resistance in the environment. And so these are some of the issues that we face. So this graph shows the global distribution of the use of antibiotics in the world. And you can see the size of the circle indicates the amount of antibiotics that's used. So today now we use about 10,000 tons of antibiotics on a global scale, and most of the consumption is in the Asian countries like China and Southeast Asia. But there's a prediction that this number is going to increase by about 33% until towards 2030. So we definitely have to think about, is this a sustainable way of expanding our agriculture industry? So this is important because when we use antibiotics, we also select for antibiotic-resistant bacteria. And the map to the left here is the occurrence, the distribution, global distribution of antibiotic-resistant bacteria. It's an index, so you can see, so it's a fraction of antibiotic-resistant bacteria or fish pathogens that has been isolated in around fish farms around the world. So what you can focus on here is that, again, in the Asian countries, up to 60% of the bacteria that was isolated, the fish pathogens that were isolated in these environments, were resistant to one or more of the pathogens that they are treated with. So it is indeed a global problem. It's something we have to deal with and something we have to be concerned about. So one of the reasons this is important is that if you look at the fish farm, so this could be a fish farm in the square there, we have the fish and they are associated with their microbiome, so there's a lot of beneficial bacteria in this surroundings that promote fish growth and fish health. But when we have fish pathogens entering the system, so they disturb the microbiome, they start killing the fish, they spread into the fish farm environment. When we treat with antibiotics, antibiotics are not selective, so they kill both the fish pathogens, but they also kill the beneficial bacteria in the surrounding, in the microbiome. Another risk is that some of these resistant bacteria, the black ones up there, they can spread into the environment, and aquaculture seems to be hotspots of reservoirs of antibiotic resistance, and there's also the risk that they can spread to humans, and we know antibiotic genes can be exchanged between bacteria, so there's a concern that these can spread into human pathogens as well. So this is a serious problem we need to take into consideration, and what I'm proposing here is some work we're doing in using a biological treatment strategy. So we want to use the bacteriophages to control the fish diseases, and this is something we work on in my group and in many other groups, research groups in the world. So on the left side here you see, so these are viruses infecting bacteria. So just like any other organisms, bacteria also become sick with viruses. These viruses attach to the surface of the host cell, they make a small hole in the host cell, and then they inject the genetic material of the virus, of the phage, inside into the host. So it essentially hijacks the metabolic machinery of the host, and then it encodes the host to produce new phage particles instead of more bacteria. In the end, there's an assembly of the phage particles inside the cell, and they start to develop, and the pressure inside the cell increases, and in the end, the cell bursts, and all the new phage particles are released into the environment and can infect other bacteria. In the middle here, this is a recording from the microscope, so you can see this is not just fantasy I'm showing here on the left. So if you look at the round particle in the top there, this is a bacterium that has been infected by a phage, and so this is a real-time recording of what happens inside the cell. So you see it actually does blow up, and the viruses are released to the environment. On the left side here, we have managed to catch that exactly moment in the electron microscope. So this is about 100,000 times magnification of what happens in that exact moment where the cell is killed. So apart from killing the cells, there's a number of other advantages of using these phages to disease control. One of them is that they are naturally occurring in the environment, so we can go out in the fish farm, we can pull them out, we can isolate them, we can propagate them, and then we can put them back into the fish farm and let them do their job. Another important part here is that they are pathogen specific. So they don't just kill any bacteria they run into, they only kill the specific pathogens that we're interested in removing. So if we sort of take us back to the fish farm scenario here, we have an infection or we have the pathogens inside the fish farm. We want to add these phages. They are targeting, as you can see, specifically the host, the pathogenic cell, and they leave the microbiome cells, so the beneficial bacteria, they leave them unharmed, unaffected, and we don't have any issues with the spreading of antibiotic resistance. So we have tested some of these scenarios in experimental settings. So this shows the survival of a fish after infecting it with bacteria. So that line here, as you can see, we have if we just infect the fish with a bacterium, we see 70% mortality after 3 weeks. But if we in parallel add these phages along with the feed, you can see there's different concentrations of phages, but having about 1 phage per 100 bacteria, we see a very strong reduction in mortality. So about 60% reduction in mortality because the phages are infecting the pathogens inside the fish. Another approach that we are working on here is to add these phages to live feed cultures. So some fish are not fed by commercial feed pellets. They live from small crustaceans like this Artemia up here. And these live feed cultures, they are reservoirs of pathogens. So when we take the live feed and put it into the small stages of the fish, we also introduce pathogens. So we have tried then to see if we can decontaminate these live feed cultures. So can we add phages to those cultures, let them incubate for a couple of hours? And we've done that, so you see to the left or to the right side here, the number of Vibrio pathogens before and after the treatment. And we can reduce the number of Vibrio pathogens in these live feed cultures by about 93%. So that's another sort of strategy, another approach that we have been working on. One of the really important things about this, I think, and what makes it, in my eyes, very promising, is that not only do we have a strong specific infection, but we also see that the bacteria that becomes resistant to these pathogens, they lose their ability to kill the fish. So phage-resistant bacteria, you see here the sensitive wild type in the agar plate to the left, it makes a spreading, a large colony on the plate. The resistant mutant that is not infected by the phage is not able to do that. Also, the sensitive wild type on the number 3 there, it secretes enzyme that can be used to degrade the fish tissue. On the other hand, the phage-resistant one is not able to do that. So we do see a loss of virulence, so the phage-resistant cells are not able to infect and kill the fish. So on the one hand, we see a effective or efficient killing of the host. On the other hand, we see that the selection for resistance is not really a big issue in this case. So the way we see this applied is, well, we produce the phages in bioreactors, purify them, coat them either onto fish feed pellets, use them to decontaminate live feed cultures, or use them to coat on biofilters, which is systems that's used in recirculated aquaculture systems. And the reason for coating them will be to prevent the pathogens from colonizing these surfaces and be maintained within the system. So to summarize some of the applications that we see here, so we think we can use one phage or one phage cocktail in many different steps in the production cycle. So either as biocontrols or decontamination of eggs and live feed, or as feed additives in the early stages of the fish production. So it's not really a treatment, but rather a way to reduce the pathogen load and therefore reduce the frequency of disease outbreaks in the aquaculture. So just to summarize my main points here, we think this technology is important because it's a targeted pathogen control. It can reduce fish mortality. It can hopefully reduce the use of antibiotics and therefore also the spreading and risk of antibiotic resistance. That can altogether reduce the outbreaks of the fish diseases and secure a more stable product chain. And finally, this would help maintaining or providing a more sustainable aquaculture production in the future. So with that, I would like to end up by thanking a lot of the sponsors here. So we are supported by the European Union, this project, Innovation Fund Denmark, and a lot of private companies are interested in this and investing in this, and then a lot of people who has been doing the majority of the work. Thank you so much.